Chciałabym na początek poprosić o zabranie głosu pana rektora Marcina Pałysa, rektora Uniwersytetu Warszawskiego. Zapraszam.
Welcome everyone. It's my great pleasure to welcome you in the hall of the University of Warsaw Library. Let me say that our main point of interest is today's lecture of Vint Cerf. Who is Vint Cerf? Well, Vint Cerf is an American computer scientist who, together with Bob Kahn, shares the informal title of the father of the Internet. In late 70s and early 80s, Vint Cerf worked for United States Department of Defense Advanced Research Projects Agency, very complicated name, where he played a key role in the development of TCP/IP communication protocol. In late 80s, he participated in the development of the first commercial email system, MCI Mail, connected to the Internet, and the formation of the Internet Corporation for Assigned Names and Numbers from its start. Vint Cerf works for Google as a vice president and chief Internet evangelist. In this function, he has become well known for his prediction on how technology will affect future society, encompassing such areas as artificial intelligence, environmentalism, the advent of IP version 6, and the transformation of the television industry and its delivery model. His contributions have been acknowledged and lauded repeatedly with honorary degrees and awards that include the National Medal of Technology, the Turing Award, the Presidential Medal of Freedom, and memberships in the National Academy of Engineering. Well, it's not unusual to talk about Internet revolution. It's an analogy to industrial revolution of 19th century that changed the world and profoundly reshaped almost everything, from global economy and climate to family life. Internet is already on its way to bring a similar impact. In our university, we are particularly interested in understanding this impact and explore societal and economic changes that it brings to people, institutions, and countries. A number of our departments, renowned for their research, a School of Economical Sciences, Interdisciplinary Center for Mathematical Modeling, Department of Mathematics and Informatics, are already active in this field. On its turn, Google is a global company that actively develops tools, concepts, and innovative products for the information age. It is therefore my great pleasure to announce that University of Warsaw and Google started cooperation in the field of scientific research on long-term effects of digital technologies in Poland and in Central Europe. As a leading university in this region and a global digital technology company, we both feel that our cooperation can contribute to the development of the economy and society in a similar way as partnership of Google with Stanford, Oxford, and Humboldt University in Berlin do it in other regions. So let's see the Vint lecture also as an inauguration of this cooperation. I'm very grateful that we can have together such a distinguished speaker, and Vint, please, the stage is yours.
Thank you very much, Rector. This is a wonderful location to meet all of you. I'm a big fan of libraries. I'm a bibliophile. I have a fairly big book collection. But I'm even more excited about the fact that we can get access to books online now and carry thousands of them in one single pad or in a laptop. So I am part of the revolution that's sitting on the fence between the old way of doing things and the new way of doing things, enjoying both of them. I want to reinforce what the rector has said about our cooperation with the university here. We believe universities play a very, very important role in the evolution of technology and understanding how that technology affects us as a society. And so this work with the University of Warsaw here and with the other universities that the rector mentioned, are part of Google's way of giving back to the academic community, which is where Google's technology originated. And it's also a way for us to understand more deeply how the technologies that we develop and others develop are having an impact both on the economy of the world and its social impact. My speech was originally titled Internet to Past, Present, and Future. You see now that it says more black swans. I promise you we will talk a little bit about the history of the Internet. But the reason that I changed the title is that I want to reinforce what's happening in the world of technology. The Internet and mobile telephony and computing have all come together in a mutually reinforcing way. When you have so many kinds of technologies interacting with each other, it can often happen that surprises will occur. If you know about swans, you know most of them are white. The black swan is the surprise that comes along that you didn't expect. I believe that the technologies that we are now working with are going to generate more black swans than we ever have seen in the past. So let's find out. Let's go back in time to 1969. I was a graduate student at UCLA, and the American Defense Department was trying to figure out whether there was a different way of communicating than using the telephone. Now, you all know what telephones are. You carry them yourselves. Back in those days, there were no mobile phones. You had to connect the telephone to a wire, and you had to dial a number, and the telephone network connected you to the other phone with a dedicated link that stayed occupied until somebody hung up. This was a very inefficient way of using the telecommunication system. So the Defense Department said, maybe we could connect computers in a different way. Maybe we could use something that we now call packet switching. I'm not going to go into details about how that all works, but for the simplest way for me to describe what packet switching is to ask you to think about a postcard. Because postcards have a to address, and they have a from address, and they have some content. That's exactly what packets are. They have addresses saying where the packets are going, they have addresses saying where they came from, and they have some content. Everything you know about postcards and the way they work is the same as Internet packets in the Internet, except the Internet runs about 100 million times faster than the post office. So we decided to try an experiment with these 4 nodes, and it worked spectacularly well. But the size of the equipment that was needed to do this was astonishing. This was the size of a refrigerator, and it was encased in heavy metal because the company that made this packet switch knew that it was going into a very hostile environment where there were students, graduate students and undergraduate students in a university, and everyone here who appreciates this knows that this is a very hostile environment in the information technology world. So they built this in a very heavy metal case. We even were experimenting in the 1970s, nearly 40 years ago, with mobile radio and packetized speech. Now here's what the mobile radios looked like in 1975. They were about a cubic foot. They cost $50,000 each, and they were very heavy. We had to build them into these racks, and we drove them around in the San Francisco Bay Area testing data communication in a mobile radio environment. We also experimented successfully with voice over the packet switch network. And so today, you don't think about this at all. You do Skype, you do Google Hangouts, you do all these various kinds of things with video conferencing, audio conferencing. But we were doing this almost 40 years ago, but not very much of it, because the capacity of the system to support speech was very limited. The speed of the internet at that time was 50,000 bits per second. That's what you get with a dial-up modem today. That was broadband in the 1970s. So we had to compress the speech down to about 1,800 bits per second, down from 64,000 bits per second. It didn't sound very good. It sounded like someone who might be drunk talking through the telephone. Everybody sounded that way, but you could make out what they were saying. The quality of packetized voice is dramatically improved now that the bandwidth of the network has gotten much bigger. This was probably the most important date in the development of the internet, not counting the first paper that was published in 1973. This shows you the first 3 networks that were built to connect together to form the internet. One of them was that little 4-node network that I showed you, except it had expanded across the United States and even into Europe. The packet radio network, remember the van that I showed you with the big cubic foot packet radios, packet radio network was running in the Bay Area. And we built a packet satellite network across the Atlantic to link the west coast of Europe to the east coast of the United States. Those 3 networks were packet switched, but they were very different. The delays were different for the satellite compared to the wireline network. The error rates were different, the packet sizes were different, and even the data rates were different. So the question was, can the TCP/IP protocols actually make all 3 of these networks look like they were one uniform network to every computer connected to any of them? And so we tested this system with the packet radio van going up and down in the San Francisco Bay Area, radiating packets that went all the way across the ARPANET to Europe, went back through the packet satellite network to the US, all the way across the United States, and down to University of California, Southern California, in Marina del Rey, California. And the distance between the packet radio van in San Francisco and Los Angeles was about 400 miles. But the packets went 100,000 miles because they went up and down through 2 satellite hops, back and forth across the Atlantic and the United States. And amazingly, it worked. And I remember leaping around saying, "It works, it works," as if it couldn't possibly have worked because it's software. And everybody knows it's a miracle when software works. So this is a really important date because it showed that the design of the internet would work for more than 2 networks. Well, this is what the network looks like today. What you're seeing here is how a global router views the entire internet. Each one of the different colors is a different network. There are about 500,000 networks all around the world that are connected together. And what's interesting about this is that there is no central control. This is a completely distributed, completely voluntary system. Each network operator has a different business model. Each network operator chooses what hardware they're going to use. They choose what software they're going to use. They negotiate to decide with whom they will interconnect. It is completely and totally a collaboration. And I remember when there were some diplomats who wondered, what would an information society look like? And someone said, the internet looks like an information society. And their first reaction was, who is in charge of the internet? And we tried to explain to them that nobody was in charge. It was a collaborative, global collaborative activity, and they refused to believe this because they didn't think anything on this scale could possibly work the way it does. But in fact, this really is a grassroots, bottom-up, fully distributed system. Here are some of the numbers associated with the net. There are an estimated 1 billion computers on the network that are servers for you. They're web servers, they're email servers, they're YouTube video distribution servers. There are about 1 billion of these machines that have names and dedicated internet addresses, numerical addresses. That doesn't count the machines that are episodically connected. So your laptop and your tablets and your mobiles are in addition to that 1 billion machines that are servers. It also doesn't count the machines you can't see. So they're hiding behind firewalls. Like at Google, we have a large number of computers. You don't actually see them on the net, but when we're serving you, we're activating those machines that are hiding behind the interfaces to the rest of the public internet. The number of users is estimated at about 3 billion. Now you know why my title at Google is Chief Internet Evangelist. My problem is converting another 4 billion people to become part of the internet community, so I could use some help. We're almost halfway there. The other thing which you all noticed, of course, is that mobiles have become a part of this environment. About 7 billion of them, but since not everyone in the world has a mobile, some people have more than one. The thing I want to emphasize to you about mobiles and the internet is how much they reinforce each other's utility. The smartphone is already a very powerful programmable device. The internet, of course, has an enormous amount of information and computing power. What makes these two so powerful together is that the mobile lets you get access to the internet no matter where you are, and the mobile's applications make use of the computing power and information of the internet. So these two systems are really mutually reinforcing. Incredibly, they were both started in the same year, 1973. A man named Marty Cooper designed a handheld mobile in 1973. It weighed about 3.5 pounds. It was about this tall, including a whip antenna, and the battery lasted for about 20 minutes. Now, I asked Marty, doesn't that seem a little short? And he said, no, it weighs 3.5 pounds. You can't hold it up for more than 20 minutes. So it was very well matched. Of course, today we put them in our pocket, and we expect them to last at least for a day. So the internet and the mobile world actually began at the same time. The mobile system in the United States was turned on in 1983, the same year that the internet was turned on. And so we have been tracking each other for decades now, and now we're seeing how powerful it is that the two systems are interworking. Now, there are lots of other things happening to the internet, and the reason I put these things up is I want you to understand that even though the internet was designed 40 years ago, it is still evolving, and there are still opportunities for people to make changes to it, to make it work better, to make it do different things. So this is not a static system. This is a system that really invites people to put their ideas to work. That's the reason the internet has grown so quickly. It's because so many people around the world have added their ideas to the design and implementation of this system. Now, there is this one little embarrassing thing. Bob Kahn and I did the original design in 1973, and we asked ourselves, how many things do we have to connect to the network? And we really didn't know the answer. We didn't even know if this was going to work. But we had just finished building the ARPANET, that first packet switch experiment. So we said, well, how many networks will there be in every country? And we guessed there would be 2 because they were pretty expensive, but there should be at least more than one for competition. Then we wondered how many countries there were in the world, and we didn't have Google to ask, so we had to guess. And we guessed at 128 countries because that's a power of 2, and that's what computer scientists think in. So we said 2 times 128 is 256. That's 8 bits. And then how many computers will each network have? And we guessed 16 million, just to be really generous. So that was a 32-bit address, 4.3 billion terminations. And this actually worked all the way up until 2011. And in 2011, we ran out of the what's called IP, Internet Protocol version 4 address space. Now, fortunately, we worried about this problem in the 1990s and invented a new format for the internet packets, those little internet electronic postcards, with 128 bits of address space. 3.4 times 10 to the 38th, 340 trillion addresses, which should last until after I'm dead, and then it's somebody else's problem. So we introduced IP version 6 formally and officially last year on June 6th. So you are now beginning to run the 21st century internet in parallel with the 20th century internet. The version 4 and version 6 are running at the same time. We estimate by the end of this decade that about 80 to 90% of the world will have managed to implement IPv6 as well as IPv4. Something else worried a lot of us, and that is that for many years the domain names of the internet, like www.google.com, were only written in Latin characters. And we thought there are other languages in the world that you don't write with Latin characters. Russian, Japanese, Chinese, Arabic, Hebrew, Urdu. There are all kinds of languages, and so we have now introduced into the domain name system the use of all of the characters of what's called the Unicode system. So most languages in the world can now be used to express domain names. The top-level domains of the internet have been a fairly small number, like .net, .com, .org, and then about 250 country code top-level domains, like .pl or .de or .fr or .us. But many people thought there should be more generic top-level domains. So the Internet Corporation for Assigned Names and Numbers, over a period of years, opened up an opportunity for people to propose new generic top-level domains. 2,000 of them have been proposed, and ICANN is in the process of introducing those into the Internet system. Security has always been an issue in the Internet, and the domain name system is certainly one area where security could be improved. And so we have been implementing something called domain name system security extensions. And without getting into too much detail, we're basically saying when you do a lookup of a domain name in the domain name system, what you get back is a numeric internet address saying, go to this place, go to that web page, or go to that host in order to get what you're looking for. We're now digitally signing the response, so you can be sure when you get an answer back, someone hasn't forced you to go to the wrong place. We're doing similar things with the routing system in the network to increase the, I will call the integrity of the routing system and the integrity of the domain name lookup system. The last two items on the slide refer to sensor networks and the smart grid. This is going to be a really big part of the internet in the future. More and more devices are going to be on the network that are measuring what's going on in our surrounding area, the heating and ventilation and air conditioning in this room, the environmental conditions, the state of the city, what's traffic doing, the state of our bodies. All of these sensors will become part of the internet environment. In the United States, a project that was started about 6 years ago is to design and build electrical appliances that are part of the internet. So you can remotely control them, so that you can tell them, please don't use electrical power right now. We're approaching a peak load and we don't want to have a blackout. So please don't heat the water for a little while. Please don't run the dishwasher for a little while, and we'll keep the power system from collapsing. So this is part of the design of a smart appliance environment. Now, I started out by telling you that the black swans were things that were unexpected. And I want to give you a few examples from history. One of them, I think, is the printing press. The ability to reproduce large quantities of text instead of having to painfully by hand copy manuscripts was utterly transforming. Although if you study history, you'll discover that the effects of the printing press invention in the 15th century didn't really show up for a couple of hundred years when books became more widely available and motivated people's interest in learning how to read. So some of these black swan events take time to have their apparent impact. The transistor was invented in 1947. That was quite some time ago, and yet we are seeing the rapid evolution of devices using transistors. This was an absolutely transforming event, certainly for computing and for communication. I think internet is another black swan. And one of the interesting things about the internet's design, which we were very conscious of choosing, is that the packets that are part of the internet don't know how they're being carried. So they don't, it's like a postcard doesn't know whether it's going in a train or a boat or an airplane or on the back of somebody's rucksack. The postcards don't know how they're being carried. The packets of the internet don't know. They don't know if they're on a radio channel, a telephone wire, a satellite link, or an optical fiber. And they don't care. The reason this is important is that since 1973, every new communication technology that has come along has been swept into the internet to support it. So what this allows us to do is to future-proof the internet, to allow it to take advantage of any new communication technology that comes along. Now, postcards don't know what's written on them. The internet packets have no idea what they're carrying. All they know is that they have a little bag of bits that they're supposed to take from one place to another. Because the network doesn't know what the applications are, you don't have to change the network when you build new applications. So all of the interesting things that happen in the internet happen at the edges where the computers are that are interpreting the bits that are flowing through the system. Which means that if you have a new idea for a new application, you're free to put it onto the network. You don't have to change the internet. You don't have to negotiate with every internet service provider because the network is completely neutral and agnostic about the applications. So these two features of the internet have allowed it to expand in scope, applications, and speed over the decades that it's operated. The mobile itself is another example of a black swan phenomenon, the smartphone in particular. And the reason should be obvious. The people who write the applications for the mobiles don't have to know anything about all the details of how the radio works, how the mobiles work, even how the internet works. All they have to know is how to write programs that properly interface to the mobile's operating system. That's all they have to know. And so this information hiding is a very powerful way of allowing more and more people to invent applications without having to have too much detailed knowledge of how everything works. 3D printers are the next black swan. Some of you probably even have them already. Basically, this is a transforming idea. Instead of making something and shipping a product somewhere, the 3D printers let you send the design to the 3D printer, wherever it is, and the 3D printer makes it at the end. Now, of course, you still have to bring raw materials to the 3D printer so it has something to print with. But the idea of sending the design and sending the physical object is a real black swan, and we are just beginning to see the implications of that. Some of you may have heard of a little computer called Raspberry Pi. It doesn't cost very much. I think it's about $25. The thing that's important is that while there have been many computers, small and inexpensive, with very powerful operating systems, this one has really caught everybody's attention because it's an inexpensive platform for experimentation. And so we're seeing a lot of people getting these little Raspberry Pi computers and inventing new ways to use them. It's another example of the way in which the black swan phenomenon surprises us. Another thing which I want to emphasize, and part of the reason this collaboration with Google and the university is so important, is that digital economics are utterly transforming. What do I mean by that? Well, think about newspapers for a moment. When newspaper was invented, it turned out to be very inexpensive, and it was the cheapest way to get a lot of information out to people on a regular basis. You would print the newspaper and people would deliver it. Now along comes the digital revolution. Bits are cheaper than paper. Bits are cheaper than print. We can distribute bits far less expensively than we can distribute physical objects, DVDs, newspapers, magazines, and so on. So the business models of companies that were dependent on cheap paper have to change because the digital revolution dictates that. If you've ever studied Darwin, you know that he only gives us two choices: adapt or die. And in the business world, when the economics change, that's the same choice you have: adapt or die. So we are watching companies with old business models learning to adapt to the new economics of the online world. In the case of Google, advertising has really been the driver for our business. In the newspaper world, everybody would see the same advertisements because once you print them on the paper, you can't change them. But in this digital world, we have flat screens whose displays can change at will, which means that when Google puts up an advertisement, it's specific to the person looking at it. That is a big difference from the standard advertising model. And so that's one of the reasons that our company has been so successful, because we're showing people things that we hope that they are particularly interested in. It's rather funny in a way. Many people tell me, I never click on any of the Google ads. And I think, well, somebody must be clicking on them because we generated $50 billion worth of business last year. Here's something else that we are in the midst of. Some of you have a Kindle or an iPad or a Google Nexus tablet, and you read books on them. Now, one of the interesting things about those technologies is that if you're like me, you need reading glasses, and I don't have to wear the reading glasses if I can make the font big enough. But you know what happens when you make the font bigger? The number of pages in the book goes up. So the organizing principle behind books, which was page numbers and paragraphs and sentences, changes in the online environment. So we are forcing a long-term standard model of identifying where information is in books. We're forcing it to a new model. I'm not even sure yet what it's going to be, but it can't be page numbers if you keep changing the number of pages in the book, depending on the size of the font or the size of the window that you're looking at. And finally, another example of digital economics. When you start running networks at 1 billion bits per second, like we do in Kansas City, it changes the way people think about the movement of information in the network. A lot of people watch video today, and they see streaming video. What this means is the network is delivering the packets at just the right time so that the video is nice and smooth and the audio doesn't break up. But when you're running at 1 billion bits per second, you can download an hour's worth of video in 10 seconds. So why bother streaming? Just download the whole file and then play it back whenever you want to. That's the kind of behavior pattern that I'm anticipating as higher and higher speed networks become part of our environment. Now, there's another thing coming. It's called the Internet of Things. These are devices that you wouldn't normally expect would be part of the Internet environment. Picture frames, refrigerators. I remember thinking, what would you do with an Internet-enabled refrigerator? Well, you could have a nice touch-sensitive display on the front of the refrigerator. I don't know whether Polish family life is like American family life, but historically, the way we communicated with each other was to put little pieces of paper on the refrigerator with a magnet. But now, with this nice high-resolution display, we can add blogs and web pages and Twitter tweets and other kinds of things. But you know what else we could do? If the refrigerator is connected to the Internet, and if everything that we put inside the refrigerator has an RFID chip on it, the refrigerator could figure out what it has inside. So while you're at school or you're off at work, it could be surfing the Internet looking for recipes that it could make with what it has inside. So when you come home, you would see a list of all the recipes that you could have for dinner. Now, this sounds like a rather nice outcome. You could even extrapolate on this. You might be on vacation, and you get an email, and it's from your refrigerator, and it says, you put the milk in there 3 weeks ago, and it's going to crawl out on its own if you don't do something. Now, the Japanese have done a very bad thing. They've invented something called an internet-enabled bathroom scale. When you get on the scale, it figures out which family member you are based on your weight, and then it sends that information to the doctor, and it becomes part of your medical record. That's probably okay. But what if the refrigerator is on the same network? And when you come home, it says, here are the diet recipes that you should be making. Or maybe it just refuses to open because it knows you're on a diet. So much for the idyllic life. Now, you see on the right-hand side there, mobiles. We all have those. We know they're part of the Internet of Things. I used to tell jokes. I said, someday every light bulb will have its own internet address. I can't tell jokes anymore. Somebody sent me an IPv6 radio-enabled LED light bulb. And so now we make light bulbs that you can control remotely. You can test to see if they're still broken or not. And by the way, although they're expensive, they cost about $20, but they last for 15 years. They don't have the same degradation characteristics as an incandescent light bulb. So this is another piece of the Internet of Things. And you see one of our founders, Sergey Brin, wearing Google Glass. Now, I want to tell you about Google Glass for a minute because this is a very exciting capability. Now, the first thing you need to know about Google Glass is that it doesn't do any more than your mobile does. So you could imagine strapping your mobile to your forehead. I can tell you that wearing Google Glass is more comfortable than strapping the mobile to your forehead, but it basically does the same thing. It has a camera, it has a microphone, it has a speaker, although in the case of Google Glass, it's a bone conduction speaker. It actually delivers sound through your skull. And of course, it has a display. Here's why this is such an interesting piece of equipment. The computer sees what you see, and it hears what you hear. And so it becomes a part of your context. Here's something we can almost do. Imagine that I have a blind German speaker, and I have a deaf sign language speaker, and they're both wearing Google Glass, and they want to communicate with each other. Let's see what happens. So the German speaker says, Guten Nachmittag, ich heiße Vint Cerf. Good afternoon, my name is Vint Cerf. Now, the deaf guy doesn't hear this, but the Google Glass has a microphone. It hears the German, it translates the German into English, and it displays the English text in the little display that you see over his right eye. So the deaf guy sees what the German speaker said. Now, the deaf guy responds with signing. Of course, the blind guy can't see that, but the camera on his Google Glass sees the signs, translates the signs into English, translates the English into German, and speaks the German in the bone conduction speaker so that the blind guy hears German speech. Now, like I say, we can almost do all of that. The only thing we can't do very well is recognize the signs, but it's just a matter of engineering. I don't want to minimize it, but I believe it's entirely possible. So we actually have the possibility of making computers our partners in our spoken and visual environment. This is the beginning of a grand exploration of making computers more useful for all of us. Here's another example. I mentioned earlier sensor networks. I have a sensor network in my house. It uses little radios that are running IP version 6. They use 2 AA cells, and they last about a year. And they are sampling the light levels, the humidity, and the temperature in each room in my house every 5 minutes. And they transmit that information through a self-forming radio network to a system that I have in a rack of electronic equipment in my basement. Now, I know, only a geek would do this. But the idea here is at the end of the year, I have good engineering information about how well the heating and the ventilation and air conditioning has worked, so I know how to adjust it. One of the rooms in my house is the wine cellar. There are a couple thousand bottles of wine in there, and I want to keep them below 60 degrees Fahrenheit, and I want to make sure the humidity is above 40 degrees, or 40%, because I don't want the corks to dry out. So that room is alarmed. So if the temperature goes above 60 degrees Fahrenheit, I get an SMS on my mobile saying your wine is warming up. One time I was away for 2 or 3 days, and every 5 minutes I kept getting a little note saying your wine is warming up because the cooling system had failed. So I called up the people who make this. This is a commercial product. This is not me in the basement with a soldering gun. And I said, do you make remote actuators? And they said, yes. And they said, great, do you do strong authentication? Because I don't want the 15-year-old next door to mess around with my wine cellar. And they said, yes. So that was a little weekend's worth of work. So I got to thinking, you know, I can actually tell if somebody's gone into my wine cellar when I'm not there because I can see that the light went on. But I don't know what they did in there. So, you know, I thought, what if I would put an RFID chip on each bottle, and then I could do an instantaneous inventory to find out if any bottles have left the wine cellar without my permission. And I was explaining this wonderful design to one of my engineering friends, and he said, you have a bug in your design. I said, what do you mean? Well, you could go into the wine cellar and drink the wine and leave the bottle. So now I'm going to have to put sensors in the cork. And as long as you do that, you might as well sample the esters that make the taste of the wine to figure out whether it's ready to drink. So before you open the bottle, you interrogate the cork. And if that's the bottle that got up to 90 degrees one day, that's the bottle you give to somebody who doesn't know the difference. So this is a very practical thing for me to have. In all honesty, all buildings, all offices, all automobiles, all residences, apartments, and separate dwellings will have these kinds of sensors in them because they will help us be more conscious of how we are using electricity, how we're using other consumables, and how our choices of behavior affect the environment and how they affect our bill at the end of the month. So this will be a very common part of our environment. Now, Google has been experimenting with self-driving cars. The short story is that the Defense Department challenged universities to develop a car that could drive itself. You could see why the military would be interested in that. If they don't have to have people driving the cars, they can have more cars out there or more vehicles. So they launched a grand challenge. The first year, nobody won. All the cars ended up in the ditch. The second year, Stanford University won. The third year, Carnegie Mellon won. And so, of course, Google hired the teams at Stanford and at Carnegie Mellon, and now they work at Google in our moonshot department, Google X. I want to show you what we're actually doing with the self-driving cars. This is one of our blind employees taking advantage. Could you run the, could you run the video for me, please? This man has lost 95% of his vision. He's officially blind. There's the self-driving car with the LiDAR rotating on the top.
How are you? Doing just great. Go ahead, Steve.
Auto driving.
Here we go. Away we go.
This is pretty scary.
Look, Mom, no hands. No hands anywhere. No hands, no feet. No hands, no feet. No nothing. I love it. So we're here at the stop sign. Yep. Car's using the radars and laser to check and make sure there's nothing coming either way. I find myself looking. Old habits die hard, man. They don't die. Hey, anybody up for a taco? Yeah. What do you want to do today, Steve? I'm all for tacos though myself. All right. Well, let's go get a taco at the drive-thru. And we're turning into the parking lot. How neat. There we go. Now we kind of creep along here. Does anybody have any money? I've got money. No, I've got my wallet right here. You roll down your window and order a burrito. Yeah, push that up. I'm doing very well. How are you today? This is some of the best driving I've ever done.
These are just everyday chores.
95% of my vision is gone. I'm well past legally blind. You lose your timing in life, everything takes you much longer. There are some places that you cannot go, there are some things that you really cannot do. Where this would change my life is to give me the independence and the flexibility to go the places I both want to go and need to go when I need to do those things.
Okay, thank you. You can kill the video.
You guys get out. I've got places I have to go.
Now, I have a challenge here because I actually want to get some time for a Q&A. And these topics could easily take up the rest of the month. They're huge issues associated with the internet. So I'm going to try to just summarize. When the general public got access to the internet, this sort of started in the early 1990s as the World Wide Web opened up. And in a very interesting way, the internet today is a mirror of the global society that we live in. When we look in that mirror, we see some things that some of us don't like. We see people who commit fraud, we see people who cheat, we see people who do a lot of other things. And yet, the problem of looking in the mirror is that you don't fix the mirror. You have to fix what's reflected in the mirror to deal with issues and problems that you see. And so this is not necessarily something that the internet can fix. It's something that we have to fix as human beings on this planet, living in the societies that are more interacting together than they ever have before in the past. So privacy and safety are really important. If the internet isn't really safe, and if it isn't really private, then many of us will be afraid to use it, and its utility will dissipate. So companies like Google and others are working very hard to improve the security and safety of the internet and the privacy of the network. I'm going to leave it at that and say that this is going to be a long and big challenge because we use technology without realizing what the social consequences are. Let me give you a small example. Every one of us has a mobile with a camera. And we take pictures and we upload them to the net to show people where we've been. The thing is that when we take those pictures, sometimes other people are in the pictures. We don't even know who they are. And when we put those pictures up on the net and someone else sees them and says, oh, I know that person, and they write their name down, and someone else is looking at the net and sees this picture and says, oh, that person told me that they were in London, but actually they were in Warsaw. So now this person whose picture ended up on the net is in trouble because one of us posted the picture without thinking about the possible side effects. Our technology has gotten way ahead of our social notions of behavior, our social conventions. And so we're going to have to work through what the social convention should be for the technologies that are available to us, and that's going to take some time. I do want to bring up this last point, though, digital vellum. Some of you, every single day, create really complex files because you used a word processing program or a spreadsheet, or maybe you made a presentation, or maybe you were developing a computer game, or you were working with big data. Every time we create these complex digital files, we create a potential hazard, because if the software that knows what the bits mean in the file isn't available at some point, then the information is basically a pile of rotten bits because they aren't interpretable anymore. Now, let's play a game. Suppose it's the year 3000, and imagine that you've just done a Google search and you've turned up a 1997 PowerPoint file. Now, let's imagine you're using Windows 3000, just for the sake of argument. The question is, does the Windows 3000 know how to interpret a 1,000-year-old file? And the chances are pretty good that it won't be able to do that. And this is not a complaint about Microsoft. Even if we were using open source software, it isn't clear whether that software would be preserved for 1,000 years so as to be able to correctly interpret the file. And even more important, the software might not run on the operating systems of the day, of the year 3000. So the problem we have is not only preserving the digital bits, which, by the way, we know how to do really well. There are new technologies coming that will preserve bits for 10 to the 20th years. Now, of course, we haven't tested it for that amount of time, but we can estimate that. The problem is not preserving bits. The problem is preserving their meaning. And so we are going to have to think about preserving information by preserving software, by preserving operating systems, by preserving the descriptions of the computers that those operating systems ran on. I call this aggregate of things digital vellum, reminding us that we do have vellum manuscripts that are 1,000 years old, and we can still read them, assuming, of course, you can read Greek or Latin or hieroglyphics. So we don't have a regime right now that will preserve this information. So I'm worried that our descendants in the 22nd century will have no idea about what our lives were like, because all of the bits that we created with mail and blogs and everything else will have been lost because the software won't be there to interpret the data. We have a real problem to solve. Some of it's technology, some of it's policy, and I'm hoping that some of the people in this university will tackle that problem and help us save our history for our descendants. I'm going to skip over this slide just because of time. I do want to give you a quick update on what's happened in the interplanetary internet. This is not a Google project, but Google has allowed me to work on it. I started this work with my colleagues at the Jet Propulsion Laboratory in 1998. Now, let me explain what happened. In 1997, a small robot was landed on Mars called Pathfinder. The previous successful landing on Mars was in 1976, the Viking system. And so that was like 23, I'm sorry, is that right? I'm doing the math wrong. I've gotten all the, 1997 minus 76 is 21 years. So it had been 21 years and many tries that failed before we got another vehicle onto Mars successfully. Now, the way we communicated with the vehicle on Mars was with a point-to-point radio link. There's a system on Earth called the Deep Space Network. This consists of 3 70-meter dishes. One's in Madrid, one's in Canberra, Australia, and one is in Goldstone, California. And as the Earth rotates, these big 70-meter dishes look out into the solar system and communicate with spacecraft that are out there. So we got to thinking about how you communicate with these devices. And one problem, pretty obvious, is that if you land a device on the surface of Mars and Mars is rotating, eventually you can't talk to it because it's not visible until it comes back around again. Now, we haven't figured out how to stop the planets from rotating. So if we can't do that, the question is, can we build a system that will let us communicate with these devices no matter where they are on the planet? Well, let's see what happened. In 2004, do you remember, 2 rovers landed on Mars? And the original plan was to have the rovers transmit data straight back to Earth from the surface of Mars, just like the Pathfinder. When they turned the radios on, they overheated. And so the first reaction was, well, we better shut them down or not use them as much, because we don't want them to harm themselves or the other instruments that are on the rover. Well, the scientists were really unhappy about that because the data rate that we could sustain was only 28 kilobits a second. Not very much. But one of the engineers said, you know, we have satellites in orbit around Mars that were originally put there to map the surface of Mars to figure out where to put the rovers. But they finished their work. We have another radio on the rovers that can reach the satellites that are overhead, and they can transmit at 128 kilobits a second. So we reprogrammed the rover and the orbiter. So the orbiter now became a store and forward relay. So as the orbiter came overhead, the rover sent the data up to the orbiter, and the orbiter hung onto the data until it got to the right place in its orbit to send the data back to the deep space network. It was a tiny little packet switch network. So my colleagues and I said, why don't we design a network that would span the solar system and support manned and robotic space exploration? We started out thinking that we ought to use TCP/IP because it works on planet Earth, so it ought to work on Mars. We very quickly had to discard this idea. The way the TCP protocol does what's called flow control is to say to the other guy, I've run out of room, please stop sending. Now, if the other guy hears this in a few hundred milliseconds, this works very well. But Earth and Mars are 20 minutes apart at the speed of light when they're farthest apart in their orbit. And when they're closest together in their orbits, they're still 35 million miles apart. At the speed of light, it takes 3.5 minutes one way, 7 minutes round trip time. The TCP flow control just doesn't work with 7 to 40 minutes of round trip time. So that's problem number one. And the other problem is because the planets are rotating, we have the problem that the connection, a direct connection, will be broken. So we designed a whole new suite of protocols that we call delay and disruption tolerant networking protocols that overcome these side effects. They are now on board the rovers, they're on board the orbiters, they're on board the Mars Science Laboratory, they were on board the Phoenix lander that landed in the North Pole in 2008 and only lasted for about 90 days. And we also put them on board a spacecraft called Epoxy, which is in orbit around the Sun and which has rendezvoused with 2 comets in the last decade. So we have a nascent interplanetary backbone. This is what we are, whoops, wrong way, here we go. This is what we hope is going to happen. We're standardizing the protocols for space communication with the Consultative Committee on Space Data Systems. It's a United Nations organization. All the spacefaring nations are members. If they adopt the use of these new protocols, then every mission that gets launched will be compatible from the communication point of view with every other mission. Just like when you plug into the internet, you can talk to 1 billion machines because of the standard protocols. So if the spacefaring nations adopt these protocols, every time we launch a new mission, eventually it can become a node in the interplanetary backbone. So we're not trying to build this big network and hope that somebody comes. What we're trying to do is let the network grow in a very organic way. And that's what we anticipate will happen. Now, that's not the end of the story. This is the last slide for anybody that's getting nervous. Here's a new project. The organization that originally funded the ARPANET, that funded the internet, that funded the architecture of the interplanetary backbone, that funded the self-driving car program, has now funded a project to design a spacecraft to get to the nearest star in 100 years' time. Now, that would be Alpha Centauri, and that's about 4.4 light years away. Now, there are a few little problems to overcome. The first one is propulsion. The current propulsion systems that we have available would take 65,000 years to get to Alpha Centauri. That's a little long, even for an ARPA project. So we're going to have to design an engine that can get up to about 20% the speed of light. Right now, I'm betting that that will be a high-powered ion engine. We'll have to carry enough mass on board to run for 100 years. And oh, by the way, after the 50-year mark, we'd better flip the spacecraft over and slow down, because otherwise we'll go flying through the Alpha Centauri system and get one picture. That would be a very expensive picture. So we believe that we can design a propulsion system that will let us get up to 20% the speed of light. The next problem is navigation. You know the stars are not actually where we think they are because of the speed of light delay to see their light. So typically when we send a spacecraft into our solar system, when you get partway through the mission, you do a mid-course correction. And the way that works is you send a signal by radio to the spacecraft telling it what to do, and then you get a signal back saying what happened. Imagine that you have a spacecraft that's 1 light year away. It takes a year for the signal to get there and another year for you to find out what happened. This is not very interactive. So we're going to have to outfit the spacecraft with the ability to navigate on its own. Fortunately, we know what the proper motion is of stars that are within about 10 light years of Earth. And we also know there are stars much farther away whose position doesn't change much, even if you move 4 light years away from Earth. And so we'll use those to orient the spacecraft, and it will navigate its way to the destination. The last problem is communication. How do you generate a signal that will be visible or detectable from 4 light years away? So one possibility is to use a laser. Now, there are different kinds of lasers, but pulsed lasers can compress a huge amount of energy into a small amount of time. There are lasers called femtosecond lasers, 10 to the minus 15 seconds, a really, really short burst. So you could take 100 watts worth of power, compress it down to 10 to the minus 15, and get a really big spike. That we should be able to detect, except for one problem. Even if it's a laser, the beam is going to spread over a 4 light year distance. So by the time it gets back to our neighborhood, that beam is about the size of the solar system. It's really attenuated. Now you know why I need the interstellar backbone. I need to build a synthetic aperture receiver about the size of the solar system to recollimate the beam and bring it back and detect the signal. But there is one other possibility. One of the physicists in the program said, you know, gravity bends light. That's how we figured out that Einstein's theory was correct. When there was an eclipse of the sun, you could see the light from a star move close to the sun by a predicted amount. So if we go 550 astronomical units away from the sun, it's about 55 billion miles, we're at a place called the sun's gravity lens. That's where the lens of the sun would bend light to a focal point. So all we have to do is get a spacecraft to go to that location, and it will be able to see the light from Alpha Centauri being collimated back into that focal plane. Now, there is a little catch here. The only spacecraft we've ever sent anywhere near that far away is the Voyager, and it's only 13 billion miles away, and it took 33 years to get there. But this is a great opportunity to test the ion engine that I was talking about. So maybe before 100 years is up, we'll send a spacecraft 55 billion miles from here to test the theory about the gravity lens. Okay, that's up to the minute status of the Interstellar project. I'll stop there. I'll thank you very much for your time. I'm happy to try to answer questions, and in any case, I really appreciate the opportunity to spend time with you this afternoon. Thank you.
Vint, thank you so much. And now we have a real challenge, because apart from all the participants that we can see in this room, we also have participants from other countries. Wow. And other, due to the power of new technology. So let us meet them, and let me introduce other participants, other groups. So here we see University of Children, alumni and students who gathered in Wrocław. Oh no, sorry, everything is now different. Let me look, have a look, sorry. So this is Czech Republic from Prague Google office. And these are people from the Leading Economic Institute, and also people from Startup Yard, Seed Accelerator for Technology Startups. And now we see Google Wrocław indeed, yeah? And these are alumni and students from Children University, which is quite a unique project. This is about getting children's imagination heightened by participating in various university events, like, for example, special workshops and also special lectures. And now we are in Sunrise Valley, which is in Lithuania, and these are people who lead a startup hub. So who is next? Hello, who is next?
There we are.
Ah, there we are, Bratislava. So welcome, Bratislava. And thank you, American Chamber of Commerce, for hosting our group. Let us now move to Croatia, I guess. Yeah, am I right? Hello. So this is due to the courtesy of the US European Business Council. Do we have anybody else to meet? No, not really. So now let us be our University of Children from Krakow, I guess, this time. Yes? Hello? So now we have to be very, very effective because we have quite few groups ready to ask questions. So let us do it in such a way that we will have one question from somewhere else and one question from our room. And let us start from Czech Republic. So may I have your questions that needs to be very concise, very short, and the same concerns answer.
Hi, what do you think about the idea that the internet should be free of charge for everybody?
I'm sorry, I'm having some trouble hearing this. Say it one more time.
What do you think about the idea that the internet should be free of charge for everybody?
Well, I wish that we could make it free of charge. There's a little problem here. It costs money to run the internet. But we should keep in mind that the way it gets paid for does not necessarily mean that everyone has to pay for everything. Here's an example. At Google, we offer all kinds of services free of charge, but somebody does pay. It's the advertisers who support our business model. So in a way, we are getting some things for free. Let me also point out that when you buy access to the internet, you don't have to pay for everyone else's access, just yours. The person that you're communicating with buys their access to the net from an internet service provider, and then the two of you can do whatever it is you want to across the network. So although we aren't quite at the place where it's free, we're at a place where it's pretty much a bargain.
Thank you. And now it's time for our group here. May I have your question? Who is the first? Okay, I see there somebody.
I wanted to ask you, what do you think about the open source, decentralized value transfer protocols like Bitcoin and the others? It's been a big thing recently, and as you're the father of TCP/IP, I would like to ask you, what do you think about the TCP/IP for the financial system? How it's Bitcoin is called.
Okay, so you asked a lot of questions all bundled up together. First of all, I'm very uncomfortable with the Bitcoin idea. And the reason I'm so uncomfortable with it is Bitcoins don't have a fixed value. They vary dramatically. And if I wanted to have a financial system to either pay for things or to receive payment, you never know what the value is of what you got, because tomorrow morning it may change by going up or going down. So I don't find that to be a very persuasive way of doing commerce. I'd like to have more certainty in the value of the exchange. Well, with regard to TCP/IP in the financial system, there is more to the financial exchanges than just those protocols. And in fact, you need to add to them a variety of cryptographic methods and strong authentication techniques in order to make sure that the banking transactions are properly protected. If you look at the SWIFT network, for example, you'll find a heavy utilization of cryptography. At Google, we strongly believe that people should have what's called two-factor authentication. This means that when you're logging in and using a username and password, the system still won't accept your login unless you also produce a cryptographically generated password, which we call a one-time password, because you only use it once. When it cannot be reused again, the system won't accept it. You have to have a little chip that you plug into a USB port, or you can have a program running in your mobile that will generate these cryptographic one-time passwords. So between the use of cryptography for confidentiality and the use of cryptography for strong authentication, we think those ingredients can put together an extremely strong and protected system for not only financial transactions, but all kinds of personal interaction as well. So Google is investing heavily in introducing cryptographic methods throughout our system, including between the data centers on our optical fiber networks, to prevent some of the problems which have surfaced recently, which I'm sure everyone is familiar with when Mr. Snowden was describing what the National Security Agency and some of the other intelligence agencies have been doing with Google and Yahoo and Facebook and some of the other internet-based services. Thank you. It's a good question.
Thank you. Now it's time, as far as I know, for the University of Children question. Let us have your question, please.
Powiedział pan kiedyś, że sen jest stratą czasu, więc ile godzin dziennie pan śpi?
You're quoted saying that sleep is a waste of time. So our question is, how much do you get to sleep actually?
No, we're having trouble hearing that.
Let us have
Maybe we have to get closer to the microphone?
Yes, please.
Hi, Vint. You're famously quoted saying that sleep is a waste of time. So one of the children's questions is that how much actually do you get to sleep?
How much? I'm sorry, we're both having trouble hearing this.
how much you sleep a day?
How much do I sleep? Sleep is a waste of time. That's what she just said. It's a terrible thing. You know, ever since I was a young boy, I hated to go to sleep. And now as I've gotten older, I don't need as much sleep, and it's wonderful. I think it's God's way of allowing you to make your life last a little longer, because now instead of sleeping half the time or a third of the time, I only sleep a quarter of the time, and I have 3/4 of the day to experience the last years of my life. So, if you can avoid sleeping, it's a good thing. You can sleep after you die.
So now it should be easier because it's turn for your question, please.
Thanks for dropping by to Warsaw. I have a question. What do you would imagine a Web 4.0 would look like?
So I was having enough trouble figuring out what 2.0 and 3.0 were. Some of these things are, marketing terms. But let's imagine for just a moment where we are today. We know that the web is something that we typically interact with keyboards and mice. We're starting to interact with it with voice. Google and others are allowing you to speak to your mobile or speak to your computer and get answers back. In Google Glass, for example, the commands are spoken, and the responses come back in the bone conduction speaker as well as on the display. So let's imagine what Web 4.0 might be like. It could be that we will get to the point where we can use gestures. We may get to the point where we might have a more cognitive interface with our network. Let me give you a very short example of how this might come about. Have you ever heard of something called a cochlear implant? This is something that helps a deaf person hear again after being profoundly deaf. Basically, it puts electronics in the inner ear that allows a computer to hear for you and to electrically stimulate the auditory nerve and make the brain think that it's hearing. It is hearing, but it's hearing by pulses that are generated by a computer. So this is what's called a sensory neural interface. We're starting to also see what's called sensory motor interfaces. These are implants that go into the spine. If someone has a spinal cord that's been damaged, you can relay the signals around the damaged spot and make legs and arms work again. This is very early stages now of research and development. What I'm hinting at here is that we might get to the point in Web 4.0 where we can actually understand what people are thinking. I don't think this is going to happen anytime soon, so you shouldn't lose any sleep over that.
Thank you. And now let us move to Lithuania. What is your question?
Hello, we have no questions, so I guess we just save our time and let others to ask. Thank you for a great lecture.
Okay.
Thank you so much. So now it's again the question. Yes, thank you.
You mentioned that TCP/IP by design was transport and content agnostic. How do you envision the future when sometimes governments are too powerful to stop resisting the control or censorship?
So this is a question which is on many people's minds. Cryptography is, of course, one of the tactics that can be used on an end-to-end basis in order to hide information while it's in transit or even when it's stored. And that's probably the strongest tool we have. The problem with censorship is that it inhibits the kind of communication that we want in democratic societies. One of my good friends is Esther Dyson. She says that the remedy for bad information is not censorship, but more information. So I believe that there will be and have been attempts to censor the internet. Some of them will be successful, but in the long run, I think that people will find ways around this. There's a sort of tongue-in-cheek expression by a good friend of mine, John Gilmore. He says that the internet interprets censorship as damage and routes around it. And I think that the engineers who make the internet work and who are evolving it are very much aligned with the idea that we should have freedom to hear and freedom to speak in this online environment, and they will do their best to assure that that's the case.
Thank you. And now let us move to Bratislava. Please, may I have your question?
Hello, thank you for a wonderful lecture. I'd like to ask a question about quantum computers. How do you see it, how do you see their use in the future of the networking and computers as such? Because it's supposed to have multiple powers, multitudes of power of the current computers. How do you see the year? Where are we going to use them on a daily basis?
So I'm missing one or two really important words in the question. Can you help me with that? You wanted to know how I saw something, and what was the something?
Computer.
And quantum computers. I was asking about the quantum computers.
Oh, quantum computers. Okay, thank you very much. If you miss one word in a sentence like this, everything else doesn't make any sense. Google is actually really interested in quantum computers. We have one. We are working together with NASA using a machine called the D-Wave. And that machine, although there have been arguments about whether it is actually a classic quantum computer or not, it's actually what's called an adiabatic system. We have shown that for certain kinds of algorithms, it does show the classic expected speed-up of computation. It doesn't do this speed-up for everything, but it takes advantage of the fact that entangled bits retain all states. And so when you're doing a computation, you're actually doing the computation on every possible value of what's called a qubit. So we believe that there may be some real advantage in making quantum computing work for certain kinds of applications. The ones that we care the most about are, for example, Bayesian computations. There are people who rightfully worry that if a quantum computer can be built to do factoring at extremely high speed, then most of the cryptographic algorithms that rely on the factoring of the products of large primes being hard will no longer be satisfactory to prevent people from cracking the cryptographic codes. And so there's a lot of work going on now trying to figure out what's the alternative to the existing cryptographic algorithms if quantum computing is successful. My honest belief is that there's so much evidence now that quantum calculations can be done that we have to anticipate that they will become common practice and common use. In fact, we're beginning to see the possibility of quantum computation at ordinary room temperature. This would be an absolute black swan of all black swans, because today most of them have to run at very, very cold temperatures near absolute zero. So we can all anticipate, I think, in the next 2 decades, some very, very big surprises coming in the quantum space. Thank you very much for asking that question.
So let us be back to Warsaw.
We have one right down here, if you like.
Powiedział pan, oczywiście pan reprezentuje firmę Google. Jak pan myśli, czy Google się utrzyma jako lider na rynku internetowym? Wiadomo, że biorąc pod uwagę kapitalizację, Google jest plus minus drugi na świecie po Apple'u, no ale Apple nie jest firmą internetową. Pytanie moje jest takie, czy Google boi się, że ktoś inny wymyśli wyszukiwarkę, na przykład Yandex, ale Yandex jest oczywiście dużo mniejszy niż Google. Proszę o pana opinię na ten temat. Jaka jest pana wizja? Dziękuję.
Okay, thank you for that. First of all, Google is a huge fan of competition. We believe that competition makes us work harder. We know that if somebody comes up with a better algorithm than we have, for example, for doing search, that our users will go over there, and that will have a negative impact on our business model. You are seeing some other things happening at Google. We are branching out in a number of different dimensions. We are building gigabit fiber networks in the US and also in Uganda and Africa. We own now mobile mobility. We make mobile phones. We release open source software deliberately to enable other people to build products and services. We believe that the more capability there is out there to use the internet in effective ways, the better it will be for us and others. So Google is actually pretty interested in staying ahead by running as fast as it can, but we know that there isn't any place to hide, that the capital value of the company is no substitute for innovation and creativity. So our model is take risk and run as fast as you can. And if you're lucky, you'll stay ahead of everybody else. But we know that we have to keep running.
I am afraid that we only have time for the very last question.
Okay.
And please, Ivan, yes?
Hiya, you had a great presentation. Thank you very much. The thing I would like to ask is that the goal of companies like Google is to provide free internet access and information to everyone. So that service is limited for a few large providers, or to a few large providers. What would happen if those companies denied access to certain countries or groups? I know it's a hypothetical question, but could this happen in the future? And if it does happen, what implications would it have on society at large? And could it ever be prevented?
I'm sorry, Ivana, I was not able to understand all of that question. The sound quality was pretty tricky. The interpreter, were you able to hear? No, he couldn't either. And he's not hearing impaired like I am. I'm really sorry. Do you want to try in very brief terms? I know you mentioned society. Are you asking about the impact of internet on society and my predictions, or something else?
I mean, you can answer that question if you like. Yes, the impact of internet on society.
All right. So I think actually the people in this room are more likely to be able to answer this question as well or better than I can. Let me say one more time that we do not yet have an intuition about the impact of the technologies we're using on our social environment. There are people, for example, who point to the Arab Spring, and they say, look how powerful these technologies were. They induced political revolution. I think that we should not be too proud of that. I think we should be careful to recognize that these powerful tools for organizing activity, which are often very powerful and very positive, have the following potential hazard. If everyone decides they want something to happen, then they have different motivations for wanting that to happen, but they all agree this must happen. But they haven't figured out what to do afterwards. then you have a real problem on your hands, because you've taken an extremely powerful social tool enabled and supported by the internet, and you've made something happen without thinking 2 or 3 steps ahead. And so I think as a society, we have to recognize that we're using tools today whose consequences we have not fully understood. This is why the study of social networking and societal behavior is a very, very important subject for us to explore. And that's one of the reasons I'm so glad that our relationship with the university here includes the economics group as well as the mathematics and science groups, or computer science groups, because we need all of that perspective in order to understand what's happening to our society. People tell us that you often don't recognize what's going on in history when you're living it. You can only see it from some distance. I think we hope that we can see it sooner rather than later, so we can guide ourselves in a direction that's constructive. So I hope, Ivana, that was an approximation of an answer to the question we were guessing that you were asking.
Yeah, thank you very much. Great presentation.
Thank you.
Thank you.
Thank you very much, and I'm sorry, but we do not have time for any other question, but I believe that this very last question was quite interesting, because it's back about the mirror and ourselves looking into that mirror, and your opinion that we should do something about ourselves instead of looking at internet as a kind of the deus ex machina power that leads us to somewhere.
That's right. I mean, we can use technology to solve some of these problems, but a lot of the problems are us, and we have to figure out how to change our own behavior. And that's a problem for every one of us today.
Yeah, thank you so much, but I will not be able to forget about interrogating the cork in my bottle. I think it's... So thank you very much, and I invite you to see the exhibition prepared by the Center for the Citizenship Education. It's really very, very revealing and very nice. Thank you very much.
Thank you very much. And I think a lot of people